Welcome to Modern Application Development online event. Today we're going to go through three topics. Moving from a monolith to a microservice, and how would you deploy on modern technologies such as containers, event-driven systems, and orchestration. My colleague Gabe Hollenbay is going to talk through how to build orchestration and workflow using AWS step functions, a managed state machine. And finally, Matt Fitzgerald, Principal Evangelist, is going to talk through how to use Event Bus and eventing systems to be able to build messaging systems so that you can scale your microservices. So join us on these three talks today, and we'll talk you through building a modern application deployment. Hi, and welcome to Modern Application Design. This is Building Effective Services with Sean Ray. I'm Senior Manager for Developer Evangelism in AWS. And today I'll be talking through the business cases and how we build a modern application. So in the agenda, we have the business case. So why are businesses actually building modern applications? Why do your business people care about the fact you're building modern applications? We're going to talk through the three common architecture patterns: monoliths and microservices, event-driven systems, and workflow orchestration. And my colleagues after me, so Matt and Gabe, are going to talk through these last two architectures in great detail. On number three, we're going to talk through the operating model. So once you have moved to microservices, there's a whole bunch of operational considerations you need to do. So how do you deploy? What's the right abstraction? And how do you monitor everything once you've deployed that? And finally, we're going to talk through software delivery. Now that we're in an age of microservices where things have their own deployment pipelines, how do we effectively manage those hundreds of microservices at scale? So the business case for modern applications is really driven actually by your end customers, by the business that your company is in. And it's not necessarily driven by IT projects. CIOs and CEOs are being told by their boards that they need to do digital transformation. And Gartner has done surveys and found that 47% of CEOs are being told that they have to change their business from their board. 79% of CIOs are saying that they need to actually do digital transformation to be effective in their business. And 67% of all business leaders believe they must up the pace of digitization to remain competitive. So there are pressures coming from the business as you as IT people are going to serve. And that means that we need to build our applications in more agile ways and more cost-effective ways so that we can actually address those concerns from the business. And the way that we think about this and the way that we remain competitive is the innovation flywheel. So the idea is that we take something that is not too risky and we experiment with it. We build a small piece of code or an application and we show that it returns value. So we don't go out and do a multi-year project. We don't go out and spend $100 million. We do something small, something that's critical to the business, and we experiment with it. From that, we get feedback. Was it successful? Did we measure the right things? And then we use those ideas to scale through the business again. So now, instead of doing one application, we're doing 50, or we're building a whole new interface to our mobile application. So we want to start with a small experiment, show value, and then scale it through the business. And some of our customers have already been on the modern application development journey. So FICO, they reduced their overall compute cost by 95% by moving to a serverless orchestration platform. The Coca-Cola company, they cut their processing time from 36 hours to 10 seconds for putting the nutrition labels onto their cans. And FINRA, which is a financial regulator in the US, they built a stock trade validation system in just 3 months, whereas previously it was taking them over a year. The Washington Post, newspaper publication, they are now doing 50 deployments per hour. So they have a huge velocity in putting out changes to their business. And this is part of that innovation flywheel that we just talked about, where you want to experiment and then move up the cycle. So they wouldn't have started at 50 deployments per hour. They would have started at some other number and then optimized until they got there. And so what defines a modern application? What does this term actually mean? What we've found from our millions of customers that are on the AWS platform is that they're generally built on containers and serverless. They've generally gone for a microservices architecture and they're distributed in nature. Each component is autonomous and independent, meaning that you can deploy it separately. You don't have to wait to deploy other applications. And finally, you can actually monitor those applications. So things like distributed tracing and open monitoring, so that we can understand that when someone does a user request from the front end all the way through the database, we can actually see what's going on for the total performance of the application. So how do we actually get there? If we're in the current world and we have been told that we need to innovate, our CEO and our CIO are telling us to, what do we actually need to change as IT practitioners to be able to build a modern application? So the three things we need to look at today are architectural patterns, how are people building these applications, what the operating model is, what cultural changes, what operating changes do we need to make so that we can actually run these applications, and finally, what do we need to change in our software development practices, either with our developers or with our DevOps practice if we have one of those set up. If we look at the architectural patterns that are very common at the moment, most people start with a monolith. And the reason that you start with a monolith is you need to understand what your business is. And so some companies have been around for many decades and they have a huge monolith that they have one big deployment artifact and they put it into production. And sometimes that means that the releases are much slower. But Martin Fowler, who writes extensively about microservices and monoliths, says that you should start with the monolith first. If you're a brand new company or you're setting up a brand new division, you might not necessarily know what the boundaries are for you to break something into a microservice. So building the monolith is actually a good way for you to understand the business problem. And on the other side, we have microservices. So the monolith does everything, and everything is contained in that one package. In the microservices side, we start to build different services for different interactivity. It's probably easier if I display it a little differently. If you think about the monolith generally has one package, so a jar file or your type of application file. It normally has a shared database. So you're having one database with everything managed. So accounts, users, reporting, all in that one database. It quite often has a shared interface. So you might have an API, but the API does users and accounts and payments and reporting. It has shared logging. So one nice thing about a monolith is generally the logging is all in one place. So you don't need to worry about distributed tracing and other types of operational concerns you have when you go to a microservice. And it has a single deployment. So if you know how to deploy the monolith, then you can deploy all the packages at once. On the microservices side, we have it a little bit differently. We do have our application code for that microservice, but it is only doing that one thing. It's only the user concern or the account concern. We have a data store, and different to the monolith, we generally have a data store per microservice. So the microservice that owns a particular piece of data, it might own user accounts or it might own billing. It actually owns its own database. And other services do not talk to that database without going through the public interface of that microservice. It has a custom interface. Because it has a custom interface, say on payments, then you can actually build specific functionality for payments, such as batch payment or reporting, without having to worry what the rest of the interface is doing. It has its own logging. And often when you get to 100 microservices, you start to realize that you've got a lot of different logging patterns. And so you start to standardize. So you won't have the standardized logging that you get out of a monolith. And finally, it has its own deployment logic. It's very common that when you move to microservices, there's different teams who own different services. And so what happens is that they have their own deployment logic. One team might be writing in Go, another team's writing in Java, another team might be writing in PHP. And so they will have different ways for you to deploy that service. And so you start to end up with different deployment logic. So it's nice and loosely coupled, meaning that they can deploy independently. However, if you're the ops person and you have to deploy these three microservices, you now have three different ways of doing it. And if you look at those architecture choices and the design patterns we were talking about before, then you can see on the left-hand side that the monolithic architecture has the UI, the business logic, and the data access layer all kind of contained in that one package. And then they'll generally have their shared data store. And on the right hand, we have our user interface, which could be your JavaScript or your native application. And then we have our microservices underneath. And each of them have their own messaging patterns. And so we have to be aware that some microservices don't talk to the UI and some don't actually talk to the databases. Some microservices only talk to other microservices. And so to build out the architecture and to draw that architecture out becomes a little bit more complicated. But it does mean that if accounts is way more busy than payments, we can scale it separately. And in the monolith, you can't do that. You have to scale the monolith up or across for all components, which means that you normally have utilization where one part is really busy and one part is really slow. And so you're not utilizing your resources well. And what a microservice architecture looks like. So a common pattern is that you'll have your clients, which we have on the left here. They could be mobile or IoT or the actual web client, and they're coming into a front-end API. And generally the way that you access microservices is through an API. So this might be a REST API with JSON, it might be some kind of gRPC API. And then the microservice will do certain things with that data. It might go off to a persistence data store, it might talk to another microservice, or it might emit an event in an event-driven system. And this is actually the same interaction that you'd be getting out of a monolith, except that the microservices is just doing its one thing and doing it well, built on the Unix philosophy. And as we go through that architecture, you'll start to see some common patterns. So if we map that to a business, you'll see that we have a consolidated API gateway up in the left. And this means that it might be a managed service. And the reason that people choose a managed service for API gateways or they create their own is because there's certain things you need to do once you start having a public-facing API. You might need to do rate limiting. You might need to have access keys, so only certain people can get to certain parts of your API. And so instead of managing that at each microservice level, companies often choose to actually use a managed API gateway so that they can consolidate those types of access patterns. We have our little microservices here in the blue honeycomb icons, and then we have our databases at the back. So this is for an e-commerce application. So you can see we have the store web front end, we have inventory query, we have shipping, when's it going to ship, we have an account lookup so that we can authorize you, and then they each have their own databases. And you'll see there that account lookup and shipping query actually talk directly to each other without a user interaction. And so you'll start to see that microservices don't necessarily need to have public interaction to start doing things. And this is a common business use case. Any of the companies that are out using Drupal and other types of things for e-commerce often have this type of setup. Once we have decided that we're going to go microservices or monolith, we have to be able to deploy that application somewhere. And so I'm going to take you through a little bit of history about what the deployment options are and then what the trade-offs are of each of them. So if we start with physical servers in a data center, we can fit as many as we can fit into a rack with as much power as we have, and then they become our servers. So we can have 6 servers, they're physically constrained, and we can split them up. If it's a monolith and we're doing managed state and we don't have a load balancer, then realistically we can only use one of those servers and utilization might be low. Then came virtual servers. So these are your VMware and your Citrix Zen servers and other virtualized type servers. So now we didn't have to worry about the fact that we had CPU limitations or memory limitations on the host. We could start to do things like make test environments with 1 CPU and 1 gig of memory. And we could start to utilize the servers right up to capacity. But only to the point where we could actually say, right, this application actually needs 4 CPUs and 10 gigabytes of memory. If it ever only used 1 gigabyte of memory and 4 gig, even though it had already been assigned to that VM, we couldn't really take it back away. So it meant that you had to be really good at understanding the capacity of your applications. And if you had peak time, that meant that you had issues where you needed to scale up really fast and you still might hit those physical limits. And then finally, since 2006, when AWS launched, we've had the cloud. So virtual servers in the cloud where you call an API, the provisioning time is a minute or so, and then you can have hundreds or thousands or 10,000s of these servers. And so the idea with cloud computing is that you get high utilization because you're only using servers when you need them. It means that you have faster provisioning speed. In my own experience, where I used to work before Amazon, it used to take us about 12 weeks to get a fully provisioned server that was on the internet, and now you can get one of those in 1 minute. You also get improved uptime because the vendor is actually managing the patching and the hardware and the failure of this and those types of things. It means you can use it for disaster recovery because now you can clone those particular applications and move them to other servers very quickly. And finally, you get hardware independence. You don't really care what the hardware underneath the actual virtual server is. That's a problem for the actual vendor. There are a couple of trade-offs when you move to the cloud. So one thing is, if your company is very used to spinning up a project and using capital expenditure to buy in servers, you're going to be switching to an OpEx model. So you have to understand that you will need to talk to your accounting team, your finance team, and say, hey, we're going to have a line item every month about what we're going to spend on the cloud. You can't just allocate me a certain amount of money upfront in CapEx that I can draw down on. The other thing is you'll have more scale. So with more scale becomes more responsibility. If you have a new data science team who has some data and it currently takes them 12 hours to run, but they decide they want to run it in 1 hour, they can absolutely do that in the cloud by scaling up to more servers, but then it obviously increases the cost over that period. You can use elastic resources. So if you happen to be in a business where you have one big peak day, maybe a flash sale, you can scale all the way up, and the next day you can scale down, and you only pay for what you use. After the era of computers, we started to get into containers. And containers is a hot topic right now. And really what containers are is it's an immutable object that contains your code, the dependencies, and your runtime. And the reason they became popular is it allows us from a virtual server capacity standpoint to put 10 containers or 100 containers. And so we can get that utilization much higher than we can with a virtual server. It also means that the runtime is separate from the operating system. So if you deploy software that needs to deploy on Windows and Linux, or you want to test locally on your MacBook, you can now do that with containers like Docker containers because you are abstracting the operating system away from your actual code. And so that made containers very popular. It means that you can local test things like microservices where you might have a whole bunch of dependencies that you need to rely on, and they're nicely baked into that container. And so after you've chosen whether you're going to go virtual servers or not, you'll most likely choose whether you want to go containers or not on top of that. Containers are excellent for stateless applications, applications that need lots and lots of horizontal scaling. They're generally still in kind of immature states depending on the networking for whether you want to run databases and different things in containers in production, but they're great for local testing and getting your developers enabled across different fleets. And then we have one other evolution at the end of this computing journey, which is serverless. And serverless came from physical data centers where we wanted more utilization. Then we went to virtual servers where we needed more utilization again, and we could make smaller increments, but we still had to guess what the capacity of our application was. We went into virtual servers, and maybe virtual servers with containers. And with containers, you are still building an immutable object. So it may last 1 minute, 1 hour, 1 year. It just depends on how often you actually update that software. And with serverless, there was a push to, what if we just wanted to run a function? And we didn't know if we needed to run it once or 1,000,000 times or 100,000 times a second. What if I just want to build my code? Because with containers, you still need to understand the network and subnetting and the capacity requirements. And so serverless was born. One of the first serverless products was called AWS Lambda, and it's a function as a service. And now all the major cloud providers have a function as a service that you can use publicly. And it allows you to do things like run code in 100 millisecond increments, and you can run it once or you can run it hundreds of times a second. And the idea is that you only focus on your application. You can couple that with things like the simple notification service, which allows you to do publish and subscribe. So you may, for instance, have one notification that needs to go out, or maybe go out to 100,000 Apple phones or Samsung phones or whichever phones that you're providing. And you can use a Lambda function to trigger that notification, and it will go and talk to your 10,000 subscribers on the other end and push them a notification. We have step functions, which Gabe Hollenbein, my counterpart, is going to talk about later on today. And that is a state manager. So instead of having microservices that talk to each other and nothing orchestrating them, you can also manage the state on the way through. So for instance, if someone needs to delete an account and you need to reverse a payment, then step functions will allow you to manage that state so that you can understand that you reverse the payment and now you can delete the account or disable that account. We have queuing services. So you might want to put things on queues so that readers, a Lambda function in this case, or a container can say, hey, there's 100 jobs on the queue. I'm going to read from there. and I'm going to drag that number down and process them. And then we have API gateways, which we talked about a little bit before, where you have a managed gateway so that you can do things like caching, you can do things like authentication. So APIs are really the front door of microservices. And when you choose to do microservices, you're going to have to find a way to build an interface and a contract with your downstream consumers. So this might be that the application team or the native team needs to build iOS hooks so that they can talk to your API. It might mean that another microservice depends on your API. And you have some design choices around what you want to do there. So that is whether you want to go with things like HTTP and JSON REST, which is very common, whether you want to do something like a binary format or gRPC, and so that you can get much more volume across the wire because people aren't interacting with that API. And so you want to make sure that your API is clean, that it's idiomatic, and that you can use it in a way that is self-explanatory. So if you have a user API, then you can use a post to create a user, and you can use a read to read a user. And you can create an API that when you look at what the name of the API is, it's quite intuitive for people to use. And so you'll need to make some choices around what technology you use there. And if we look at what an API looks like, you'll see that the full kind of implementation of microservices has a few other components. So we don't just have an API hitting the front end. We generally have something like a Amazon CloudFront, which is a content delivery network. If we're sending out lots of pictures or heavy multimedia, we want that content delivery network to be able to cache those files so closer to the user so that we don't have to go back and hit the microservices every time. So we get improved latency. We want to have API endpoints that have caching so that means when a request comes in, maybe query to a database or some other type of service that we've already gone and talked to multiple microservices to get, we can actually just read from the cache if it's not too old. We want to look at things like monitoring. So we might want to see all the requests that are coming in the front door, regardless of what microservice they're going to. What's the latency coming through there? How many errors are we getting? So it gives you a nice, easy point to be able to concatenate those business metrics and then report them back. Once we get through the kind of microservices with APIs, we move into things like event-driven architecture. So this is a different way to think about traditional microservices where you might be used to doing the HTTP REST JSON APIs. So microservice message patterns and where eventing comes from is you might need to send an event you don't care about. So you might just broadcast it out, someone reads it from a queue, and then you don't really know what happens with it. There's other messaging patterns like request response. You send a message, you wait for the response to actually come back from the person you're sending it to. You have things like return address, where you are providing an address that then the third party actually sends you back a response to, so like a callback. And you're trying to, in these states, decouple the fact that your microservice needs to talk to another one. So you're generally using queues in between, and you are pushing messages and events around. So if my microservice emits an event, then I don't necessarily care who's reading it. They might subscribe to my event and read it, but I don't give them any SLA about what to do with that event. It is the team who owns that microservice who processes that event that cares about what's in that event. So with something like publish subscribe, then that is done on a much larger scale where you might have one consumer or 10,000 consumers consuming your event, and they take action based on that event. So it means that I don't need to know the API of that particular microservice. I don't need to come through the front door. I'm just listening for that event. And so when you have very busy services, or you might have a user service or an account service that all other microservices need to talk to, it means that they can just emit events when accounts are created or accounts are closed or accounts hit 30 days and you want to send them some type of marketing message. They don't need to understand everyone else who consumes them downstream. As long as they keep producing events, that means that your microservice can process them independently. We also need to be able to manage the state of our applications. If we're not using event-driven systems, then we need to be able to figure out what actually happens in failure scenarios. If I'm the API gateway and I send it to a microservice that's processing an order, and I click on there and it says, actually, we are out of stock on this item. and I've gone to 2 other microservices to get that. Now I need to cancel the order and say in the front end that you can't actually progress, or I need to remove that from your cart. And so we need to be able to process those type of requests, and we also need to be able to process failures. The CTO of Amazon, Werner Vogel, says that everything fails all the time, and we need to be prepared for that. It might be that your microservice calls another service and it's not there. It might not even be in your control in your company. Generally for payments, for instance, people go to things like credit card gateways to make payments. So you might not even be in control of that third party that has failed or has slowed down and is now causing your users issues. And so we need to understand what the sequence of tasks is. We need to understand what the dependencies on all the other downstream services are. And so the way that we do that is we try and manage state. And we need to be able to do things like retries. We need to be able to do things like try, catch, finally. Or we want to do decision trees on if this service fails, try this backup service. Or if this service doesn't give me the event I want, then I need to go and do X task. And the way that we normally do that is with managing state through something like AWS step functions in a state machine. So AWS step functions allows you to call out different compute and kind of process workers. So this might be an AWS Lambda function. It might be something sitting on EC2, a virtual machine, or it might be some other type of database or something that's natively integrated. You might be putting a message on a queue. And it allows you not to just do single execution tasks, but parallel tasks. And Gabe's going to talk through great detail how you can actually orchestrate these types of events. He's going to show you details on the different types of processes that you can use and the workflow decisions that you can manage. So I'm not going to go too far into it in this talk. We also have a couple of other things that happened in step functions, which are serverless polling. So you can now be able to poll for work out of serverless, meaning that you can do things like asynchronous calls and you can just poll back when something actually finishes. And so while this is a native part of step functions, it means that we can start to do things like decouple our microservices with callbacks instead of waiting specifically for a function to change. We also now have built-in functions so that you, without having to use Lambda, can start to do things like synchronous calls or run a batch API with our batch system where you can run a HPC workload, for instance. And so that's something to keep in mind when you're designing these systems, not just to use step functions for things like serverless and containers, but also you can start to call heavy compute. So in summary of a modern application, cloud-native architectures are small pieces loosely joined. They do one thing in the Unix philosophy, and you can either use event-driven or API-driven to choose how tightly you want to couple them to your downstream systems. Now that we have just decided our architecture, we need to understand how to operate this different type of software. If you look at the left-hand picture and you just look at that kind of logical representation of the microservices, you can't really see what's talking to what depends on what, and how do we operate all those different pieces. So there's some operational responsibility when you start to use the cloud. No more do you own the physical server and the cabling in the data center. And depending on where you go on the compute spectrum between bare metal, virtual servers, containers, and something like a function as a service, there's different ownership models. You're not operationally in control of all those different pieces. At one end in the bare metal, you're responsible for everything from the hypervisor up. And on the other side in AWS Lambda, you only really care about your application code, and all the other things like operation and security and patching are all taken care of by the vendor. So this graph shows what the operational matrix is and responsibility is for AWS services. And if you're building these on your own internal services or using other third-party applications, I kind of encourage you to draw out something like this so you can understand what you own and what everyone else owns. So we talked a little bit about serverless before. On the operational model, it means that there's no infrastructure provisioning at all. You just write your application code, you upload it to your cloud provider, and then there is no management. It just runs in response to events. It has automatic scaling, so you can set it to do 100 or 1,000 or 10,000 invocations at the same time, and you pay for value. In AWS's Lambda case, you're only paying for 100 millisecond increments, and is highly available and secure. It's AWS's job to patch Lambda, to patch the runtimes, and to make sure that it's secure when you run your code. And if you look at the span of those different types of service, you have Lambda in compute and AWS Fargate. We haven't talked about Fargate before. Fargate is a managed way to run containers where you can care less about the infrastructure. So you don't have to worry about running the orchestrator. You don't have to worry about running the master node and understanding the different tasks that you need to do. Fargate extracts one layer up, so one layer down probably from AWS Lambda, where Lambda, you only care about application code. Fargate, you still do care about what's the kind of capacity that I need to build in for this particular function, but it's fully managed on containers. We have our managed data stores, so AWS S3, so an object data store that allows you to just call an API, put your objects, draw them back out, and it's completely managed by us. You can put trillions of objects into that data store. You can draw out hundreds of gigs, and we manage that capacity for you. Amazon Aurora Serverless is a managed database that is MySQL and Postgres compatible, and it allows you to use a relational database in a completely serverless way. So you don't need to worry about connection pooling and building proxies so that you can talk to things like function as a service. And finally, we have Amazon DynamoDB, one of our oldest databases that allows you to use NoSQL in a fully managed way without provisioning capacity. Then we have the integration services, and we've talked through those, and my colleagues will be talking through those in more depth, so I'll leave them to do that. So on the responsibility side, we need to understand what we're actually managing ourselves. So this map shows you exactly what AWS manages and what the customer manages. So on the extreme, you have AWS Lambda, where you have the app code, and on EC2, we do the physical hardware and software, and then you do everything else. So depending on your application, you can kind of decide with this decision matrix how far up or down this decision tree you would like to go. So in our modern application, we have gateways, we have things like EC2, and we have Lambda. And in an operational sense, the team that runs the API gateway might be different from the team that runs the application on EC2, and it might be different from the team that is running something on Kubernetes down on the end there, or AWS Lambda. But the business doesn't really care about that. If I'm a user, I hit your website, I hit your mobile application, I try and do something, I want it to be fast and I want to get it back so that I don't have any errors. And so how do you actually tie all of those different components together? And the way that people are more commonly doing that now is called distributed tracing. So in this case, we want to be able to trace from the user journey when it hits our on-premise front end all the way through till we get the response back from the database. And we want to see actually what that means. And the way that we do that is called segmenting. So the front-end on-premise interface that we might not have migrated to the cloud yet has its own segment. The gateway has its segment, and then each component has its own segment. And so that means that we can say EC2 took 15 milliseconds and had this error response rate, and on-premise took this many milliseconds and had this response rate. So we can tie all of those together into one trace and see what actually is happening for that user. We also have something called sub-segments in open tracing. And this is where in distributed tracing, and this is where we want to understand the path of a particular system that is completely outside of our service. So something like DynamoDB, where we're relying on a third party and we care about that interaction, and it sort of spans different services. So we want to be able to record a sub-segment so that we can understand what the database is actually doing specifically. And we're going to dive into one of those use cases to see how important that is. So AWS has a distributed tracing system called Amazon X-Ray, or AWS X-Ray. And this picture you're seeing is actually a real-life customer view of X-Ray, and they're showing all of their different services here. So there's Amazon S3 on there, there's some microservices that they've built, and the green dot is basically, the green circle represents how many errors. And you'll see that up in the top kind of left, there is actually one that has 1% errors, but it also shows things like average response time. And so through this, you can start to see how complex managing microservices are if you don't have access to monitoring where you can go end to end. And we talked a little bit before about the database. So it's quite often people build monitoring systems that hit the front end of the microservice. And they don't account for the fact that they're running SQL queries in the background or hitting a NoSQL database. And if we actually use subsegments like we showed in our picture, we can start to do things like understand that we're running an execute query here in this subsegment, and it's taking 12 seconds, and everything else is taking milliseconds. So we have something that's 10 times the order of magnitude worse than what most of our customers are getting. And so we need to understand, why is that one query taking 12 seconds? And because we've actually used subsegments here on our tracing, we can start to see the big problem. We can also start to add metadata to our distributed tracing. So we can add the actual SQL query to the metadata of the X-ray trace. So here you can actually see the specific update call that they're making to the database, which is causing that 12-second issue. So by using this type of access, we can start to see end-to-end what's happening through our microservice. So we can use trace IDs, we can use the AWS X-ray APIs like we're doing here to actually pull out in batch the trace and everything that it touches on the way through. So we might be interested in the user journey, and here we can see every single activity that user is doing that's generating this 12-second problem. And this particular customer who spoke at reInvent last year actually uncovered that they had an issue not with their database, but with the way that they were calling their actual application. So they were using synchronous calls to send a whole bunch of messages. And each of those synchronous calls was waiting on the downstream message. And all of those calls were hitting the same database with the same query, causing that 12-second problem. And so by using distributed tracing and AWS X-ray, they were able to see an actual flaw in their implementation. So then they changed it to asynchronous calls, where they were just waiting for callbacks. And that 12-second layer that they were dealing with is now down to milliseconds, single-digit milliseconds, because they're now doing asynchronous calls. And so that has had a huge impact on their actual business metrics and the user experience for that particular query. The other thing that they did that was really smart was that they started to add things like member ID into their traces. So inside the HTTP context header, they could actually start to add different metrics in, like the company that person was from, the member ID of that particular account. So not only could they trace on what is the overall service of that metrics, but what is actually that one user from particular company actually experiencing. And here you can see the response times for each of one of those users. And so if you have microservices where you need to understand, hey, this customer we have an SLA with, and in customer I mean big company, and these 5 users are having an issue, you'll be able to go down to that granularity if you start to use segmentation, subsections, and use the user annotations properly. And more importantly, the business cares about the actual metrics. So we can now see the percent of traces that these people or this particular type of query is using. So instead of having to go through and trawl our logs and do a report, we can quickly see that X% of our users, or 39% of our users, are creating tickets, and some are doing contact name. And so we can see the actual API queries. So now you have an operational view of what's happening in your business by using distributed tracing. And finally, we need to talk about the delivery of software. So now that we've made all of these changes, as we discussed in the opening with monolith and microservices, each of these microservices might have a different deployment pipeline. They might be running on different technology. And so how do we manage that from a software point of view? So we also need to think about serverless, because in serverless, we're not really deploying the code with infrastructure around it, and we don't really control much of the things because the managed platform, in this case, which is AWS, is controlling some of those things for us. So traditionally, the developers would build their application, they'd put it into their one big service, and this might mean that multiple people are working on the same code base, and then we put it through the delivery pipeline. And sometimes, and in my experience, we used to have a delivery pipeline in a regulated business where QA and testing would take 4 to 6 weeks to be able to test a piece of software before we could release it. And so if your very quick change that took you 1 hour, 1 day to make is now waiting 6 weeks to get into production, that can be quite frustrating for the business. And when we move to microservices, We want to change that. We want to make it so the delivery pipeline is completely independent for each microservice. And that means that we can then move down that pipeline as quickly as possible. We can deploy when our business needs and we don't have to wait on others. And what you do if you do have something that is dependent on a second microservice is you create a feature flag. And with that feature flag, you put it into production, you turn it off, and when this dependent microservice then deploys their piece of code, you flick that feature flag on and you start making those calls. So you can start to really decouple your delivery process from your dependencies. So what we've heard today from the best practices is you need to decompose for agility, you need to automate everything, you need to use standardized tools, and you need a belt and suspenders approach. So when you're doing things like security, make sure that you do things like static code analysis. Make sure that you do security scans as part of your pipeline, not afterwards where you're doing manual testing. And finally, you want to do infrastructure as code. So in that CI/CD pipeline, what it would look like is if you're using a full AWS stack, code commit, which is like GitHub, it's basically code. For build, you'd use code build. You could use third party for things like testing. And then for deploy, you'd use code deploy. So this is moving our application from I check in the code all the way to deployment. And finally, we talked about Amazon X-Ray for monitoring. And the last thing that I want to talk about, we just said in the best practices about infrastructure as code. So now that we have this fully kind of industrialized pipeline, we also want to think about the fact that we should have immutable infrastructure. So we can now do things like using Terraform, using CloudFormation. We can actually make our infrastructure code. And if we do that, then the infrastructure is now bundled with the application. And we don't have to worry about configuring, about building out the machine and then deploying our code. We actually deployed the machine or the container or the function as part of our code. And so now when we do versioning, we have a version of our application that contains the infrastructure. And one of the ways to do that is called the Cloud Development Kit, the CDK, and it uses constructs. It can also have third-party constructs, so you can use different plugins from different third-party vendors as well, so that you can start to make an immutable construct that contains all of your application. So just to reiterate, there are already some customers going on this modern application journey. We talked about FICO and reducing overall compute costs with optimization. The Coca-Cola company, who went from 36 hours to 10 seconds by using serverless, and the financial regulator, who deployed a full application in 3 months. And if you do the things that we've talked about in here, if you get those pipelines going and you start to build immutable infrastructure as code, you can get to where the Washington Post got to, which is over 50 deployments per hour. So rapidly changing your software. Where to go to learn more? OpenTelemetry is a Cloud Native Compute Foundation incubator project. It's just a merging of two other projects, so it's still kind of in the alpha stage, but looks very promising. We've heard several vendors who are going to take this on board. So if you go to opentelemetry.io, that is actually open source distributed tracing, much akin to what I've talked through here. Werner Vogels, our CTO, has done a blog post on modern applications and how people should think about them. And finally, modern application design by AWS. So this is a website that we've put together that puts most of these concepts, the different services, and the way we think about modern applications that you can go through there. So thank you for joining today. This has been an overview of modern applications. Coming up next, we have Gabe Hollenbay, who's going to talk through managing state and how to do workflow orchestration. And then after Gabe, we'll have Matt Fitzgerald, who's going to talk through event-driven systems and how you manage event buses. So thank you very much for joining today. If you're interested in any of these topics or you want to go further, we have training, which is specifically developing on AWS. So it goes through the concepts about how you do development on AWS and interact with some of these services I've been talking about. We have our Certified Developer Associate, if you'd like to get certified once you understand the platform. And finally, we have our DevOps Pro Engineer. So this is if you want to become a certified DevOps professional, you want to talk through building those pipelines like I've just gone through, then you can go and actually take that certification and show that you know AWS. After this talk, we're going to be whiteboarding. So Gabe and myself will whiteboard through some of these topics. So please join us for that after this. Thank you for attending Modern Application Development, our online event, and we'll see you next time.
Hey everyone, and thanks for staying with us. We just watched Sean's excellent talk on modern application development and systems design, and now I've pulled Sean aside so we could have a little bit of a chat about some of the concepts that you just talked about in more detail.
Cheers. Thanks for pulling me over, Gabe.
No problem. Thanks for coming by. So first up, you've drawn a little bit of an example here that will look more familiar to people after my session, which you'll see next. But this is just sort of a simple banking system where we might have account applications that get processed, right? They might be approved or rejected. And so to process them, we're going to need to check the people's identities to make sure they look good. And those might be powered by third-party systems. And then if that all looks good, if all the account processing workflow looks good, we'll actually open up an account for them, right? This is sort of the structure we've drawn here. And there's some database that powers this. Now, when you drew this out right now, I noticed that you're drawing things with a little bit of different icons. We have this account service and as a square, the workflow processing system as a green hexagon, and we've got this identity checking system as a blue circle. So in moving from a monolith to microservices and thinking that way, how does that relate to the shapes and colors that you've chosen here?
Yeah, sure. I guess, often when you're moving to microservices, you're moving from a monolith, which is really that kind of really big bit of tin, and you're separating out the concerns and separating them into services. And so the reason I draw the boxes differently is they're actually different compute engines basically underneath and different deployments options. So accounts, you can think of this as the kind of, EC2 virtual machine. The circle I've got kind of representing Lambda, which is a function as a service that we have, and proc is sitting on managed containers workflow. And so the idea is that you don't have to have a team that has a unified technology to run these. And often we find when you move to microservices, different teams are actually now owning the code for each of these services. So they might choose their own technology choices.
Okay, and the fact that you decided in your example to say that the account service was powered by EC2 and the identity checking is powered by Lambda, that's a little bit arbitrary for this discussion. You're just trying to illustrate the great thing about microservices is that we can use different types of compute engines for each service and for what's comfortable for the team and what scales best with those service needs?
Absolutely, yeah. We don't really have a real kind of scaling example here. So, it might be that accounts is super busy and we can do it on different types of technology, and it might be that, ID checking happens 3 times a day. But we don't have that kind of workflow context here, so I just drew them out arbitrarily to show this is how we can deploy.
Okay, cool. And now, when you move from a monolith to microservice or distributed systems in general, if you don't want to call it microservices, that's also okay. You start having to monitor the system at large a bit more, and you talked about distributed tracing in your session, but I'm wondering if you can just touch on it a bit more here and talk about what are the things we need to pay attention to when we distribute our system like this into different moving parts?
Yeah, sure. Look, distributed tracing has been around a long time, and I think it was much easier before because we had everything on the same box. But now, there's lots of pushes in open source, like Open Telemetry, which I talk about in my talk, is one sponsored by the CNCF. And really what we want to do is we want to be able to understand the experience of the user all the way through the stack. And if you do have teams that are geographically separated, they're managing different parts of the system, it might take you a long time to actually get back, hey, well, how is my person performing? What is the latency that this person is getting?
And so is it important to measure just the the latency and the performance metrics between each service, or how do we get a vision of the at-large end-to-end flow also?
Yeah, the kind of purple line I drew down the side is sort of representing, I guess, the entire kind of open, the trace itself, right? So we want to go from the user all the way through and any retries or failures along the way. And then we have something which is kind of called segmentation. So each of these green arrows represents one segment of how our user is actually going through. And when we get to sort of some other parts like these 3 Ps over here, which represent third-party APIs, it's often with the ID checking, you use a third party.
Sure.
Then we can start to do things such as sub-segment where we're actually saying, hey, third-party 1 is actually slower than third-party 2. we're now going to weight our traffic differently based on the fact that I can see users are starting to get affected.
Right, so you're saying that if to check somebody's identity, I might use two different third-party providers that give me the same service, and I might be calling them both every time I need to do an ID check and figuring out which one's performing better right now, and I could feed that information real-time back into my identity checking service so it could prioritize them maybe.
Absolutely.
Okay.
And I think the other thing that I see in tracing is people often stop kind of at the service front end, at their HTTP API. And really with the way that the libraries are getting to now, you can start to do things like put the entire SQL query if you've got a relational database and actually start to see what it's actually pulling out, why it's taking 2 seconds to actually process. And I talk a little bit about that in my talk. So you can start to roll that up into business metrics of creating an account takes X and this particular third party is giving us this performance. So you start to get a whole view of your application much easier.
Awesome. That's really helpful. And the last question I wanted to ask you is, if we notice in this diagram, this sort of account application processing node, it's kind of at the center of everything here. And so, I think that makes sense because this is a thing involving it's going to fulfill the request for, hey, I would like to open a bank account. Great, let me check your ID. Let me then open up an account if everything looks good. Maybe let me get a human involved in reviewing before I approve it or whatever. Yep. How do we manage this sort of this orchestration or this collaboration between all these services? If he's in the middle, is this the point of fragility here?
Yeah, I think this is kind of the service that is reliant on all the other services around it. And the way that we would normally do that is some kind of managed state machine. So we have AWS step functions, which I understand you're going to talk about after this particular video.
Yep.
And you could put all of this in yourself and write it and rewrite failure logic and retry logic. But the reality is that in a modern application, you used to be using some kind of managed state machine to take some of that pain away from you.
I couldn't agree more. In fact, it was a leading question because that is exactly what I'm talking about in my next session. So stay with us and you'll learn more. Data store now. I've made a bunch of color powered by something called state machines. If you don't know
in yourself and write it and rewrite failure logic and retry logic. But the reality is that in a modern application,
I'm a senior technical evangelist. Hello, and thanks for joining me for this webinar. My name is Gabe Hollenby, and I am a senior technical evangelist here at Amazon Web Services. And in this session, in the next 40 minutes or so, I'm going to teach you about fully managed service orchestration powered by something called state machines. If you don't know what state machines are, don't worry about it. I'll explain it. You probably already do know what they are. You just don't know them by that name. All right, let's get started. So quickly, just to cover off what I plan to discuss in the next 40 minutes. First, I'll describe very high level about getting things done with distributed services, just to sort of frame our conversation. And we'll talk about two common coordination patterns we see with getting services to communicate with each other. Those are called choreography and orchestration. Then I'll illustrate how to orchestrate services using state machines. I'll introduce you to AWS Step Functions, which is a fully managed service that we offer that lets you run state machines in the cloud. I'll give you examples in the real world of customers using AWS Step Functions to orchestrate services, and then I'll teach you where to learn more. Okay, let's talk about getting things done with code, with services, how things work at a very high level. So in a monolith, everything gets deployed together, right? And so in this slide, I've made a bunch of colored boxes to represent what might be different modules of your application. And the gray bar underneath them all would be like the data store, right? And so in a monolith, all of our code is packaged up into one artifact and deployed onto one service together. And it's got a common data store. And that's generally how most projects start out. But as things grow, you add more and more modules to your system. Eventually, you probably need to start breaking it out into separate services. And we often call that approach microservices, even if the services are not necessarily very small. So with microservice architectures, we split this big monolith up into multiple systems. And so each module that is clearly separated from each other module gets its own data store now. And the advantage of this, each of these being their own services, is we get increased agility and scalability. And let me explain what I mean by each of those. So talking about agility here, what I mean is now teams can focus just on one vertical slice, right? One service now, instead of having to think about how what their work is doing on that service connects to all the other modules, because they've already been separated out. That means that code can evolve. You could use different languages to implement these different slices of services. And also teams have their own data store, so they don't necessarily need to worry anymore about having schema changes impact other modules in the larger system. So that generally lets teams get things done faster. You also get better scalability because with microservices, each service can be tuned and scaled appropriately. That might be some vertical scaling, as indicated by these larger colored boxes, or it might be horizontal scaling, or sharding, where you have multiple copies of a particular compute process and maybe behind a load balancer or something. And even the databases can scale and even be different types of data stores to serve each service's specific needs. And so that's really great. Microservices tend to give us a lot of value, but it's not always all 100% roses in microservices land. Because big distributed systems, they get harder to coordinate and harder to debug. As these systems need to work with each other to get larger amounts of work done, specifically with workflows, it can be hard to figure out when something doesn't work, what was the problem? Where did things fall apart? You also might need to wonder about, how do I make these services communicate with each other? Should they be totally distributed, where they all just communicate via some shared message bus and they don't know anything about each other? Or maybe when a process needs to get executed in a particular workflow, maybe that should live in one place and all the other services should get invoked accordingly to that process. These are kind of two opposite style approaches to service coordination, and they're both useful. And so we'll talk about both of them in turn now. First, let's talk about choreography, and then we'll move on to orchestration. So here, to talk about this, I always like to get a little bit more concrete and give a specific example. So this is a very simplified banking system, but I picked this subject because it's something we can probably all relate to. You might have things start out with an application. I would like to open a bank account. So I fill out some kind of application, and that might be handled by this blue account application service. Now, to process the application, maybe we have a data checking service, which will do things like check the identity documentation I provide for my account application, maybe also check my address to make sure it's formatted correctly and is it actually a known place. And then if all of that looks good, then I should have an account created. And then we can zoom in here to look at that. We're not going to talk about the rest of this system. I just wanted to contextualize it, right? In this banking system, you'd also have the ability of, debiting and crediting accounts and transferring funds, and some BI layer, business intelligence layer at the bottom that might be observing events from all of these systems to give you more insight. But we can just zoom in here and say, to open my bank account, this is the flow, right? These are the collaborating services that need to exist. And probably I want to insert some human review step in here. So if the identity check or the address check comes back flagged by the data checking service, then I might want a human to step in and review the application. But maybe for my simplified example, I'll say, if everything looks good, we don't need a human to review. We can just approve the application directly and get an account created with the account service. So in choreography, we use this term to describe services emitting events or publishing events about things that happen in their service that other services might want to know about or react to. And that's it. It's very, very decoupled. You have an event bus or some kind of pub sub or messaging relay system that all the services can listen to and be notified of events that they care about. And these services will work in concert to achieve some larger flow simply based on what events they emit and what events they listen to then react to. And in that way, a whole sequence of events can correspond to a larger workflow getting executed. And so here's how that bank account workflow might happen here with choreography. I would submit my application, and we would start out with the account application service emitting an application submitted event. And then, because we need to have my identity checked, we need to emit this identity check requested event. The data checking service would listen for that event. It would do an identity check. Then it would return an identity checked event. The account application service is interested in that event, so it would be listening for that. And after it got the result of that, it would go and check the address. Of course, the same flow would happen. The data checking service hears that an address check is requested. It's going to perform that address check and emit the results back with an address checked event. The account application service is interested in that. So now it knows that the identity was checked and the address was checked. Then it could go ahead and decide if everything looks good. The application is approved. Of course, the account service would be listening for application approved events so that it can then open an account, and then it would emit a account opened event. And so that's quite a long flow, and it's a bit complicated, right? You have, it's true that these systems are all completely decoupled and none of them know about the other services at all. All they know is that some events that they care about might come onto this event bus and that they should react accordingly. And so even though they're distributed this way, there is still a coupling. There is still an awareness of events. They need to know what events each other emits so that they know which ones they need to react to. And the decoupling of this is nice, but as you can see, it does feel a little bit complex in order just to implement a relatively simple workflow here. And so there is an alternative. The alternative is something we call orchestration. In orchestration, you've got one place or one process that manages the state for your workflow, and it's just going to call the appropriate services in turn. For example, in the account application service, that would probably be where something would be responsible for ushering the whole flow of an account application. It would check the identity. It would check the address for an applicant. Maybe it would get a human involved in a review if needed. And then ultimately, if everything was good and an approval decision was made automatically or by a human, it could get the account created. And that's a much simpler workflow, as you can see. And this is probably the way that's more familiar to us because we're probably programming like this already just by writing a bunch of if-else statements in our code, coordinating with other services. And that's fine, but there's a way to get things even more robust. So before I explain how, let me just cover off when should you use choreography and when should you use orchestration. Well, based on what you've seen, you can probably agree that choreography can get quite complex pretty quickly for workflows. And so you only want to use a choreography style, fully decoupled approach where they're just reacting to events for simple workflows without much logic. Or a better piece of advice might be to think of it as use choreography for broadcast style workflows where service no longer depends on what the other services will do once it emits a particular event. You can think of it like fire and forget. For example, a nice scene might be for the account application service to just emit application approved, and then it's done. And then you could use choreography to have the account service react to that one business domain event in order to create an account. But we didn't need to implement the whole workflow in a choreography fashion, right? You can just glue separate systems together with choreography at the point where a nice, clean handoff might happen. Whereas orchestration is designed to do well at this idea of managing workflows. And you should use orchestration because you'll typically get some kind of execution auditability for your workflow. What I mean by that is because it's all managed in one place and all your business logic is in one place, it's easier to keep tabs on the flow of a particular execution of that workflow and understand what the ins and outs from each system are that you're collaborating with, and it makes it easier to debug. You'll also generally get better retry and error handling capabilities in an orchestration approach. Again, because you have one place where all of the state about that workflow lives, and you can make more intelligent decisions about how to react to possibly transient errors or other errors that could come up during your workflow execution. So let's dig a little bit deeper now into this orchestration way of doing things and see a real concrete example of processing a new bank account application in this way. And we'll elaborate on what you saw before in the sample flow. So this might be what our workflow looks like. We start by verifying my identity documents for an application. We check an address. Then we decide if we want to get a human involved in a review. We're going to wait for that review to happen if the review does happen. And then finally, the application will get approved. And that's nice, but there are some things about this workflow that we can improve. So let's evolve this a little bit more. First, this step, verifying identity documents and checking addresses, can be done in parallel. We don't need to do them in this serial fashion because checking the address has no impact on, it has no dependency on the identity document results of that verification. So we can arrange these in parallel instead. So now what we're saying is start my workflow immediately in parallel, check an identity document and check the address. They don't depend on each other. Just get both of those things done in whichever order it happens. They can happen at the same time. Wait for both of those results to come back to me, and then I'll have the information I need to decide if a human review is required. But because we can do those steps in parallel, we've sped up our system a little bit. Next, we can look at this step and say, well, a human review isn't always required, right? It's only going to be required for, in this example, if one of these checks, the identity document verification or the address check, comes back with some sort of flag from that service. And so in those cases, we'll want to wait for review. But if neither one of those previous checks gives me a flag, my simple example is going to say, fine, let's just approve the application. So let's change this workflow to reflect that. And that's it. It's a minor change, but now we can see that it's possible to go straight from the review required checking process to say, do I need to have a human get involved or not, to straight to approved. Finally, we can look at this and say, we don't always approve applications, of course. Sometimes an application might be rejected because a human being looked at something that got flagged and finally decided, no, I don't want to approve this application. So we need to add that into our workflow. And so that's what we've done now. So we've added a step that says, after we get a review, we'll look at the result of that review and see if it was an approval or a rejection. And then correspondingly, we'll either approve the application or reject the application. And that nicely sums up our entire example bank account workflow. It's a much nicer evolved workflow because we're taking advantage of parallelism. We're waiting, but only when we need to. Now, this, what you've just looked at here, drawn out on the screen, is actually something called a state machine. And that might be an unfamiliar term to you, but you're already familiar with this. You just don't know it, right? We already use the concept of state machines in our programming sometimes, even if we don't explicitly codify it as such, because really, a state machine is quite simple. State machines just describe a collection of computational steps that we're splitting into discrete states, right? So in code that we're writing sometimes when we're working on whatever systems, you're going to have different functions, and some main function might say, okay, check my data, and if the address check looked bad, then flag. If the the identity check looked bad, then flag. And then I'll say, if anything was flagged, review, etc. Right? So with if, else, and switch statements and whatnot, or doing executions in parallel, we're already familiar with this programming model, but we don't always split up our code into explicit states. But the way our code executes is often by looking at some shared state, deciding what function to call next, and moving some code or some data through our code in order to get a result. State machines just explicitly codify that into a way that's easier to draw these kind of diagrams that you saw of how everything should move through a particular workflow depending on how the data is set up. Now, state machines have one starting state, and they've always only got one active state while they're executing. And what happens is the active state gets some input, so that'll be the first state at the beginning. You're going to start your state machine by giving it some input. It will take some action using that input, and it's going to generate some output. And then based on that output, the state machine decides what's the next state that I go into. And the state machine just transitions from one state to the next based on these outputs and the rules that we define. And ultimately, work is getting done and moves us into a successful execution, or we hit some error that we don't know how to recover from, and we end up with a failed execution. But that's it. That's a state machine in a nutshell. And the cool thing is we have a service that will let you run state machines in the cloud in a really nice fashion. And it's called AWS Step Functions. It's a fully managed state machines on AWS. That's the way I like to explain it to people. You can also think of it as a way to have resilient workflow automation, running in the cloud at scale. What's great about Step Functions is because it's fully managed, we at AWS handle the high availability and the scalability concerns for you. You just define your state machines and you tell us to execute them. You give us input and say, execute, start this execution on this state machine with this input, and we'll handle the availability and the scalability for you. And we've got built-in error handling with Step Functions, which I'll talk about more later, as well as powerful AWS service integration to implement these workflows, tying in to a lot of existing AWS services to make your life easier. We also have first-class support for integrating with your own services. Now, when I first heard about Step Functions, before I even worked at AWS, I thought that maybe that was only for managing like AWS Lambda functions, right? Or the idea of code as a service, right? The serverless functions, but it's not. You can use Step Functions to help automate any process that's running anywhere. You can implement any one of these tasks that comprise a workflow in your own server on premises, even on a mobile phone, anywhere that can pull the AWS Step Functions API over HTTPS can act as a process to handle tasks in a workflow, which is pretty neat. And also, to help with the sort of debuggability and explainability of workflows with distributed systems, Step Functions makes it really easy to audit every execution history, and you get a nice visual monitoring to see how workflow executed in what path, and you can see each step, what the inputs and outputs were for each state in the workflow. And we'll see details about more of that as we go along. Let's talk about the basics of Step Functions. Here's how Step Functions works at a very high level. As you've already seen, we coordinate our individual tasks into a visual workflow. And these workflows that we build are a number of steps, and these steps are just called states. And all of these states together makes a state machine. Now, the most common kind of state, or the most useful kind, because if you couldn't do this, you couldn't do anything, is the task state. And that's what does work. And that work can either be coordinating other AWS services, or it can be working in concert with a process that you can host anywhere, as I already explained. There's a pass state, which just passes your input straight through to your outputs. That's very useful for when you're just starting to edit a state machine at the beginning. You can make all of your states just pass states so you can sketch out the flow. And then you can change each of those states later to whatever the appropriate node type is. We also have a state called a wait state, which will wait for a particular period of time that could be relative or absolute before continuing. So effectively, it pauses execution until some future time. You have parallel states, which can branch off execution and effectively do many state machines inside your larger one. And this is all still within inside one AWS Step Functions state machine definition, but then the definition can nest inside, which is very helpful for getting work done in parallel. And you've got choice states, which can look at output and decide what state do I go to next based on the state that I have in the output from my previous states. And when these state machines are executing, we're just moving from one state to another. We call those transitions. And finally, a nice point, a cool thing about using Step Functions is that by creating your states in very focused fashions, you can reuse the same task states for different workflows, giving you really nice code reusability. How does this all work? It uses something called Amazon States language, which is a fully specified language that lets you express your state machines using some nicely structured JSON. As you can see here, at the top level, you can have comments and you define what state your machine should start at. And these are just names. So we have a state called Hello World. And then you have one or more states defined inside that states key that describe different types of states, which you already know some of the types of, and how they glue together in order to sketch out an entire workflow. Let's look at this in more practical terms. Here's our example new account workflow with our diagram on the right. And let's illustrate these different types of states inside of this workflow. We're going to talk about tasks, parallel steps, branching choices, and even waiting for a callback. So performing a task can be done in a number of different ways. You can call an AWS Lambda function to do basically whatever you want in whatever language you want. And you're only going to get billed for the amount of time that that code is being executed. That's nice. Or you could wait for some polling worker to perform some activity. And this is the mechanism I explained before, where you can have code running anywhere that fulfills a task step in a state machine. Finally, if you want, you can pass parameters to an API of an integrated AWS service to get some work done. In this example, if we look at just this section here for verifying identity documents, we could implement this by calling a Lambda function. And this is the Amazon States language we might use to implement this task. So we give it a name, verify identity documents. We say the type is task. This task has some parameters. And then I point to a resource, and that resource is an Amazon resource name pointing to the Lambda function that I want to run to implement this task state. And those parameters that I'm defining are going to be the parameters that get passed on to the Lambda when the Lambda gets invoked to do this work. And you can see a little bit of a naming convention here where we use this $sign on each side of a key value setup in order to say, this is how I want data from my state machine state, in this case, an application object that has a name and an ID doc as 3 path attributes, how I want those to thread through in the parameters to the Lambda. And finally, in this case, there's only one step inside this branch of this parallel execution. So it says end true because there are no other branches there for that parallel execution that this particular task step lives under. We can also execute branches in parallel, like we were just looking at. The verifying identity documents was one branch that we were executing in parallel. And this just contains an array of state machines to execute. And we get back an output of array elements describing each of the branches that executed. So in practical terms, here's how we would implement both parallel branches here for checking identity documents and checking the address. It looks very similar, except this time the type of this particular state is called parallel, and we have a branches property that define little state machine JSON snippets inside. So it's like the larger JSON, but just you can use that same structure inside each branch of a parallel state in order to get work done. And we can say that the result for all of these different branches, we want to end up in a variable, in this case called checks, inside the larger state machine state. And the next step would be human review required. That's the name of it. And we also want to make a choice. We want to look at data and decide what step do I do next. So this is like a switch statement in programming. It looks at an array of choice expressions and it compares variables to values and decides what's the next state I should go to. So here you can see that our human review required state is a type of choice, and that's the state type. And we have an array of choice expressions that look at particular variables. In this case, we're looking at things from the checks variable, which came from our previous state. And we'll see if either one of our checks was flagged then as true, then we want to wait for a human to review. Otherwise, we'll default to approving the application. Finally, in addition to just waiting for a fixed period of time, oftentimes we might want to wait for a callback. We might want to wait for a human to get involved in this process, do something, and then continue onwards. And so we can use this concept inside state machines of a task token to do this. So with the callback interaction style, we have step functions, create a task token and pass it on to some other service. When that other service is done with its work, it calls back to the step functions API using a send task success or send task failure API call with the task token, so step functions knows what that service is talking about. And then the workflow will resume its execution appropriately. Here's how invoking that might work here with an external callback from a Lambda function. So what we would do here is we're going to say that the type is task. The resource is a special ARN string that says, I want to invoke a Lambda and wait for a task token. The Lambda will, in this case, I'm calling one called flag application for review. I'm giving it some payload. These are the parameters to go into the Lambda function execution. And you'll notice that one of those is this task token that comes from the step function state. And in this case, what this flag application review Lambda would do is store that task token in a database somewhere for that particular application ID. And then a human would have some interface where they could see all of the applications that were flagged. And then when they made a decision on it, at that point, whenever they interacted with some API, it would get that task token from that pending application that was flagged. And it could then call back to the step functions to say, here's the result that the human took when they clicked approve or reject. And then the workflow would resume executing. Okay, let's dive a little bit deeper into step functions now. I've already covered most of the state types. There actually aren't that many. Step functions is a pretty simple service once you understand the base concepts. You have seen most of these state types already, except for a few. I've talked about the wait type. Even though you didn't see it, you understand it lets you wait for a particular period of time. The map type is the most interesting one we haven't talked about yet. And this lets you process an array of input elements with a particular state machine. This is very similar to, in programming, you might be familiar with a map function, which takes a function and an array of items and applies that function to every item in the array to get back a new array of results. That's the same thing that the map state here can do in step functions. And what's neat is you can even coordinate the amount of parallelism you want in that map execution. So you can actually say, do them in one at a time, or you can say, I'm happy to have parallel execution, and you can set the maximum number of parallel executions, or say, do them all at once is fine. But this is different than the parallel state, because a parallel state says, do different things for this input, whereas the map state says, do the same state machine for each item in this input. And finally, the only other steps we haven't talked about yet are succeed and fail. Succeed just is used to semantically mark the successful end of a branch of a parallel or an iteration of map. And you've also got a fail state, which says explicitly something has gone wrong, terminate the state machine, and mark this execution as a failure. We integrate with a number of AWS services with step functions. I don't have time to talk about all these right now, but as you can see, there's quite a bit here. And what this means is that these are all the APIs that you can call directly from a step function task if you would like to. Working with step functions is really quite easy. As you've seen already, we define them with JSON. And what's neat about this is in the web console, when you write your step functions with that JSON, you get back a nice visualization of what that state machine looks like. And you didn't know this, but those earlier diagrams you saw, those were already done with step functions. So that's why this diagram at the bottom might look familiar to you, because we've already been using step functions to create some of these slides. And finally, my favorite feature about step functions is that you get to monitor their execution. So every time one of them runs, while it's running and then after it's running, you can go and see what steps ran and what were the inputs and outputs for every step, which makes debugging, especially complex workflows, really easy. Of course, things go wrong sometimes. And step functions knows this and gives you some really nice capabilities to handle retries and errors. So you can have failures happen because of timeouts, or maybe a task failed for some reason, or you might have had insufficient permissions to execute a particular step. Now, tasks can retry when errors occur using a back-off rate that you specify between retries up to a max number of attempts. And of course, if you exceed the maximum number of retries, or there were no retries that you defined for a particular step, you can catch these tasks for specific errors and transition to other states as appropriate. So there's really nice retry and catch semantics there for you to use when you author your state machines. If you want to do some development with step functions, here's some things I recommend. Check out Step Functions Local. This lets you execute a version of step functions on your own system, which can make debugging your workflows even easier, and certainly can speed up some of your workflows that way. So I recommend that. There's a binary called statelint, which will look at your JSON for your step function state machines and tell you if there's anything wrong with them. If you like using the serverless framework, there's a plugin that knows how to handle step functions really well. And finally, if you're like me and you like writing in Visual Studio Code, there is an AWS Step Functions Constructor extension, which lets you write your JSON for your state machine and get a nice live preview on the right-hand side of your editor, seeing what that step function state machine looks like, similar to what you'll get with those circles and arrows in the console. But you can have that locally while you're authoring as well, which I really like. Okay, so step functions and actions. Let's talk about some real-world use cases and customers that are doing cool things. So the Guardian News and Media Group, they've used step functions for a lot of things. I'm not going to read this whole quote to you, but it's by Paul Brown, a senior developer manager at the Guardian. And he mentions that step functions gives them reliable and automated ways of orchestrating complex queries and processes between their distributed systems, giving them more productivity and agility. And another benefit is it makes it easier to discuss solutions with non-technical stakeholders, because again, when you explicitly codify these things with step functions, you get a visual representation of that workflow. And that makes it easy for people who are not coders to understand what we're building. Here are a few of the actual services or solutions that have been built by the Guardian using step functions. They automate subscriber account deletions across many distributed systems. They can now receive customer orders while external billing and payment services are offline. And they can run ETL workloads for a newspaper fulfillment pipeline through a series of Lambda functions. These are all very common benefits and examples of cases where step functions really shine. Now, let's talk about the Coca-Cola Company for a minute. I don't have time to go into the detail of this, but you can watch them talk about it themselves. There's a YouTube link here on this slide. But every time Coca-Cola needs to make a nutrition facts label, and they have many products, so they have to do this a lot, either because their formulations change or because the label design changes, they have a workflow where data has to go through a number of steps, ultimately generating this nutrition facts label. It used to take them 36 hours to go from a change to a finished and approved label. Using step functions, they were able to cut this down to 10 seconds. That's a huge increase in efficiency. And a lot of that efficiency actually just came from this point I brought up before about being able to use the visual representation and debuggability of these workflows to help hone in on problems quicker. As you can see, the benefits they cite here were performing data validation and transformation steps with a visual workflow to help non-technical people understand it. And then as they were actually running these workflows, they could look in real time and see where they were behaving appropriately, because step functions makes it so easy to trace that execution. And that'll let you even identify problems and optimize things on the spot instead of having to troll through a lot of log files later, for example. The key benefits of step functions, to wrap up, it's a fully managed service, which means we handle the high availability and scalability of it for you. The visual monitoring and state management that you get is top-notch and makes debugging and understanding how your services are getting coordinated Very, very easy to do. It also gives you this auditable history of each execution, which may help you from a regulatory perspective if you need to prove exactly what all the ins and outs were for your service coordinations in order to meet some regulatory requirement. Built-in error handling is really robust. And finally, step functions is pay per use. And the billing model is really neat in that the billing model is based on how many state transitions your state machines go through. It's not based on time a step function takes to execute. And what's cool about that is if you have a wait step, and that wait step says, I want to wait for, in this case, it supports up to 1 year. So step functions can have up to 1 year of waiting time. You're not billed for any of that time. The step function just pauses and waits for it, and you're only billed for the state transitions. That's really powerful and can be very cost effective for a number of use cases. There was another use case by Coca-Cola that I didn't talk about where they leveraged that to great effect. So if this has excited you and you want to learn more about how to use step functions for your own modern application development, here's what I recommend. Start by looking at the Create a Serverless Workflow example online. And after that, spend a little bit of time and just read the entire Step Functions developer guide. It's not that big. As I explained, Step Functions is not actually a very complicated service, but it's very powerful. And I think it'll take you about 2 hours if you want to read the whole developer guide. And then you'll have a really good understanding of all the moving parts. And finally, if you'd like to see examples of step functions in action, we have a number of reference architectures you can look at the URL on this slide in order to see more. So that's it. I want to encourage you to continue your modern application development journey by looking at the AWS training and certification resources we have available. There's a lot of stuff out there online that we make available for you. It's definitely worth your time to check out. Keep in mind, we have an AWS Certified Developer Associate exam, and we also have a Certified DevOps Engineer Professional exam. Those are really great to help prove your knowledge on AWS topics. And finally, I personally want to thank you for taking this time to attend this webinar. It means a lot to me. I know you could be doing a lot with your time, and the fact that you chose to spend the last 40 minutes with me is really great. So thank you so much. I hope you found it useful, and please do fill out the survey that we're going to show you, because that's what helps us continue to iterate and give you the best content possible. Also, please keep in touch with me if you like. You can find me on LinkedIn or Twitter at the handle there on the screen. It's just my first and last name all smushed together. Okay, I hope you have a great day wherever you are. Thank you.
Hey, and thanks for tuning in. Thanks for watching our webinars, and we just thought we would have a little bit of a discussion around your talk, Gabe. I just watched it. Very informative, talking about choreography, orchestration, and systems. And so we've kind of drawn on the whiteboard a little bit here. So why don't we, have a discussion about your talk and some of the concepts we can dive into.
Great.
So one question I have after watching is, I just did a whole thing on microservices and kind of how you go from the monolith. But here you've kind of drawn bounded context. And I didn't really cover in my talk about bounded contexts, and I noticed you didn't as well. Maybe we should just kind of fill in the audience on how we get from microservices to these boxes.
Sure. You'll hear the term bounded context a lot in microservices land. And all we really mean by that is clear, separate areas of concern. And so I think about them the same way that when I write code, I think about having different classes with single responsibilities. And that means only one reason to change. So for example, in my system here, my account application service needs to check an address, check an identity document as part of its workflow. Mm-hmm. But I feel like those are separate concerns. They might need to change for different reasons. And so I thought, let's put them in different services. Mm-hmm. Similarly, the account applications, since it's concerned about managing workflows, it shouldn't be the thing that manages accounts. That's right. These are going to have different scalability requirements also. And so that's another reason to separate services out, is because people are going to do more with accounts than they are with the applications.
Yeah, and I guess, things like choices of compute and containers and Lambda and these other types of things, right, are kind of separate for how you would actually drill these out. That's just kind of the implementation detail of your service.
Yeah, exactly.
Whereas the bounded context is really driven by the business requirements of how the service interacts.
Yep.
So it's good. And then, the other thing that I kind of noticed in your talk was, you talked a little bit about third parties and kind of moving the workflows around. I guess we went through happy state. Like what happens if there's, timeouts or retries and these other types of things that actually affect our services.
Yeah, so that's one thing I really like about step functions is it's got that robust retriability for your tasks built in. And so even without step functions, right, we manage workflows today, but there, if we need to retry an external third-party systems call, for example, and that fails and we want to retry again, all of that idle time we're waiting as we back off for our retries, that's time that CPU is locked up and not doing something else valuable. And so by kicking that responsibility up to step functions explicitly, we free up our, well, A, we're not paying for that time in any sense of the word, not with opportunity cost or with like billable time cost. And B, it's letting a fully managed service take care of that state and retriability for us.
Yeah, that's a really interesting point. I never really thought about the cost optimization of using something like step functions because, you know, Lambda, 100 milliseconds, containers you're paying for while they're on, the actual compute costs. But yeah, if you're putting it in the parking lot while you retry, it also means if the business logic changes, right? Data checking is often done by third-party companies.
Yep.
They might disappear, they might have an outage. You know, all of those go to the parking lot and keep managed where you don't have to worry about a failed transaction and try it again later.
Yeah, you got it.
Yeah, cool. And then, you know, if I watched your talk and I didn't have any other kind of context, I'd probably say that choreography versus orchestration, you're kind of advocating for one or the other. You know, when would you say that using the other pattern actually works for what applications?
That's a great question. So yes, I mean, because my talk was focused primarily on workflows, that's why I think step functions and orchestration was the hero of my talk. And that's because generally I would advocate for orchestrating inside of a bounded context and coordinating through choreography or events between bounded contexts. And so even though here these are different services, in the context of processing an account application, it needs to collaborate with this. And so I felt that orchestrating these together made sense with a step function.
Right. That makes sense because this one cares about the failure state of this, and this one, you know, doesn't really do anything unless these two return kind of okay.
Exactly.
So, and then you have business intelligence, I guess, which is very different, right? Very loosely coupled. They're generally doing reports downstream on your data. So how would you see that kind of working with what you've got drawn here?
Right, so that's like, again, where I would advocate for choreography or events being published and subscribed to rather than orchestration where something has to remember to make calls out to some business intelligence thing every time something changes. So by publishing events, whenever significant things happen in any of these systems to some common event bus, the business intelligence service could listen to all those events and extract out good insights. For example, what's the average time between applications being submitted and approved? Or who are the people who are transferring money to each other most often? And is there anything suspicious about that we need to look into? Right? So all of these different services can just publish events and they don't care about who does anything with them. That's, I think, the best way for using events to glue your services together is, again, that fire and forget methodology.
Yeah, that's right. They don't really care about what the downstream dependencies are. They're just sending out the events.
Right.
And, you know, like in your examples, you know, things like money laundering and, you know, transactions over $10,000, these types of things, right, can easily be sent down, and then business intelligence systems can act on those, trigger alerts, exactly what they need to do. And our account systems, they don't really need to know anything about that.
Exactly. So just to be explicit, the event that the account system might publish would be transfer from A to B amount X, right? That was the event. It doesn't say event over $10,000 because by being a little bit more general about it, it lets the business intelligence layer figure out what's the interesting things. Tomorrow, if we start caring about $10 transactions, none of the code here needs to change. And that's why publishing events is a really useful pattern.
Right, yeah, so you get to a very loosely coupled system that is not dependent. So our colleague Matt is coming up next. He's actually going to talk about the other type of systeming, which is the event systems we're talking about here on the business intelligence. He'll be speaking about a service that we have, which is the AWS Service Bus. So please tune in for that.
Thank you.
Hi, I'm Matt Fitzgerald, Principal Technical Evangelist at Amazon Web Services, and we are going to be talking about event-driven service architecture with Amazon Event Bridge. EventBridge is a new event bus service that makes it easy to ingest and process data across AWS and SaaS applications. EventBridge removes the friction of writing point-to-point integrations by letting you easily access changes in data that occur in AWS, custom, and SaaS applications via a highly scalable central stream of events. With EventBridge, you get a simple programming model where event publishers are decoupled from event subscribers, allowing you to build loosely coupled, independently scaled, and highly reusable event-driven applications. Lastly, it's fully managed. So it handles everything from event ingestion, delivery, to security, authorization, and error handling. It's serverless, so no more managing infrastructure and building event bridges on top of it. If you've ever been to an AWS conference before, you've probably seen a slide like this. But I'm here to tell you that monoliths get a bad rap. Monoliths are easy to build and reason about. It's way simpler to understand how the system is going to work when all of your data is in one ASIC-compliant database and all of the calls you're making are operating against the same memory address space. Distributed systems of microservices are way more complex, but the problem is monoliths don't scale, both in terms of throughput as well as in the teams that support them. If you have big complex systems and you want to be able to effectively leverage dozens or hundreds of engineers to build features in parallel, you have to move to the microservices model, which gives you more customer value, more reliable and resilient systems, and obviously systems that scale. And lastly, we want to be able to do it way faster than we have been able to do it in the past. You saw in Gabe's session, he talked about orchestration versus choreography. Gabe used AWS step functions to choreograph all of the various components that were required in order to create a bank account. Without step functions, if we wanted to use a purely event-driven architecture, we would have to have some kind of event bus that events would transit along. The events would then need to have some kind of logic wrapped around them so we would know what to do with them and in what order. This session is not about orchestration. This is about extending that banking system for other purposes. So we talked about an event bus, but what kind of event bus? So we've got the banking application on the left-hand side, and then we have some microservices that we may want to use to augment the functionality of the banking application. Enter EventBridge. The banking application is a separate entity owned by a separate team. It is also perhaps a microservices architected system, in which we know it is because Gabe showed us, but its services are orchestrated differently, in this case with step functions, which we previously mentioned. So how do we enable other teams within the bank to take advantage of this system? Now, before we go too far down the track of working in a purely 100% Amazon EventBridge architecture, there may be situations where the system you want to integrate with isn't putting events onto an Amazon EventBridge event bus. In cases like this, you may have to poll the system, perhaps look at event logs or other metrics that you can use to infer events. You would then use a Lambda function to put those inferred events onto the event bus so downstream systems can take advantage of them. We won't be focusing on that in this session. So let's focus a little bit on the naming side of things. So in traditional enterprise service buses, they use terminology like emitters, agents, channels, consumers, and sinks. Remember, emitters and agents are the things that actually create the events. In Amazon EventBridge, these are known as sources. The channel is the event bus. The channel is the thing that transits all of the events that arrive from the sources. In the traditional model, we also had consumers and sinks. Event sinks and event consumers were simply other components that would subscribe to the event bus and take some action when the event came in. With EventBridge, these are called targets. So let's look at the basics of Amazon EventBridge. All of the components of Amazon EventBridge are boxed here in pink. You see that we have the default event bus, some custom event bus, and there's some event bus associated with SaaS integrations as well. And we have the rules and targets on the right-hand side. We also have sources. These are the sources of events that will end up on the event bus. Event sources could be other AWS services, custom applications. In our case, it's going to be the banking application. And we just talked about the SaaS applications that can be integrated to Amazon EventBridge. We have the event buses themselves. By default, EventBridge gives us a single event bus called default. We'll create a custom event bus for our demo banking application. We're not going to be focusing on event buses that are required for SaaS integrations, but be aware that they do exist. We have the rules. The rules are essentially patterns that are going to be used to match events with target actions, which is a great segue for event targets. An event target could be a Lambda function, could be a Kinesis data pipeline. It could be kicking off another AWS step functions workflow. Here's an example of the event structure. We have a detail type, which is an analog to an event category. We have the source telling us where that event has come from. And then we have detail. Detail is really just a collection of key value pairs that further describe the event. Now we know what events look like, and they're very simple. There's really not much to an event. We'll have a look at the rules and how the rules are used to trigger our targets. So let's just have a look at this event. So we've got an example here around application approved. We'll see that the source of the event has come from a DynamoDB streaming table. The detail of the event is really describing an application-specific construct, which in the case is a bank account from Gabe's application. We'll see that the detail describes the name of the account application. We have a unique identifier for that application, and then we also have the state of that application. Then we have an example rule that's being configured. Now, if you notice, rules pretty much just look like the events, but a subset. And in this case, the detail type is application approved. And within the detail block itself, we also have state approved, and approval type is auto and human. So how is this actually matched? Well, if all of the items in the rule match what's in the event, then the target will be triggered. Here's another example. In this case, the rule is simply saying, if the inbound event has a detail type of application flagged for review, then we'll trigger our target. So it's pretty simple how we map a rule to an inbound event. What about this one? So in this case, the event looks pretty normal. We have an application rejected detail type. But in this case, the example rule isn't matched. This is just showing that if we don't have a rule for a particular inbound event, if nothing matches in the rule, that is, then the event is simply dropped from the event bus. We don't do anything with it. So what does this mean? Okay, so we've got event buses, we've got rules, we've got targets. We're able to match inbound events with those rule patterns. We're able to trigger targets in response to those rules matching. This allows us to essentially connect data from other applications, be it AWS services, our own custom applications, which we just saw, which is the banking application, and those SaaS applications. We can take data from those systems and we can integrate them into other downstream systems. But we do it by writing way less code. We can ingest, filter, and deliver events without writing any custom code, which reduces our operational overhead. And also, we talked about at the very start that this is a serverless solution, so we don't need to provision any instances or any other kind of software to get up and running with EventBridge, which ultimately leads us to being able to build event-driven architectures with ease. So some common use cases, obviously taking action. So a certain event comes in from an upstream system. We can match that event with a rule. We can then use AWS Lambda to maybe call off some other, application function to take some action. We can run workflows as well. So we saw that Gabe had orchestrated his components using AWS step functions. So I could also use the events coming from Gabe's components, create a rule that will match those events, but instead of calling a Lambda function, I can trigger the execution of another step functions workflow. I could even push events into something like SageMaker or Amazon Comprehend in order to do some kind of intelligence. I can use Athena to query over the events as well. So rather than taking the events from EventBridge and say kicking off AWS Step Functions workflow or a Lambda function, I can throw them into a Kinesis data firehose, put them into S3, and then use Athena to query over those events. And lastly, I can use events for synchronizing data as well. So I can have DynamoDB being my target, where the Lambda function will process the event, put it into DynamoDB, and then we're able to keep systems like the upstream system, which is the event source, in sync with the downstream system. So let's dive a little deeper into the mechanics of Amazon EventBridge. So the first thing we're going to need to do is create the event bus. This is something we're not going to need to be doing all of the time. So we're not going to show how to programmatically create it here. If you wish to do that, the API call on the EventBridge client is simply create event bus. But we're going to show it using the AWS CLI. So the CLI is an easy way to get working with Amazon EventBridge. So in this case, Amazon Events create event bus command. We're going to pass a name that will be used for that event bus. And in this case, we're going to call it Banking Demo Events Dev. So if you run that, that's all that's required to create a new event bus for Amazon EventBridge. Step number 2, we're going to need to create some rules. Now, if you cast your mind back a few slides, you'll see that a rule is effectively a subset of an event. Right? So it's a JSON structured object that consists of various key value pairs that you're going to be looking for in the event. So just like an event bus, creating rules is not something you're going to want to do programmatically on a frequent basis. So we're going to show how to create the rule using the AWS command line interface. Very similar to creating an event bus, we use the AWS events put rule command. Now, for a rule, we need to specify a name. In this case, we're going to call the rule application submitted. We need to specify the name of the event bus that the rule is going to be associated with, which in this case, if you have keen eyes, it is not the same event bus as we created on the previous slide. In fact, in this case, it's going to be banking demo events. So banking demo events will be the event bus that the rule will be associated with. If the bus doesn't exist, obviously you're going to get an error. We need to specify the event pattern. Remember, this is simply a subset of the event. In this case, the pattern is simply saying, if I see application submitted as the detail type in the source event, then my rule will fire. And lastly, we're going to enable the rule. If we don't enable the rule and the event comes in, then obviously we're not going to invoke any downstream Lambda function or step function and so on. Once we've created the rule, then we need to associate a target with that rule. Now, in our banking application, the kinds of integrations we're working with are simply going to be Lambda functions in response to some event. So in this case, we're going to, once again, use the AWS command line interface to create our event targets. So we use AWS events put targets. We specify the rule that the target is going to be associated with. We specify the event bus name. Here we are actually using the correct event bus name, which is Banking Demo Events Dev. And we specify the targets that will be associated, the physical or tangible targets that will be associated with the rule. So in this case, it is going to simply be the ARN of a particular Lambda function, which is actually going to be the bank account service function. So that's how we create the targets. So now we've created the bus, we've created the rules, we've associated some targets with the rules. How do we go about getting the events onto the bus? Well, we have a method on the EventBridge client for that called put events. Put events takes a single argument, entries. Now, what is entries? Entries is simply an array of no more than 10 events. Now, we know what events are because we talked about them previously. That's that JSON payload that describes the event. essentially. So we can have up to 10 of those in the entries array, and we pass that array to the put events API call. What that does, puts the events onto the event bus. A couple of things to keep in mind though. Because you're passing in an array, there are some occasions that not all events will be put onto the bus. So it's important to check the response object of the put events call. Now here's an example of what the response object looks like. So the response object obviously has the entries, has an array itself called entries, which gives you the status of each one of those items in the entries array that you pass to put events. So you can iterate through that array to see whether any of those events failed to be submitted to the event bus. Obviously, you don't have to iterate through those entries straight away. You could simply check the failed entry count number, and if that was 0, then you can assume that all of those events were successfully put onto the event bus. The other thing to keep in mind with EventBridge is that it's at least once delivery. So you need to make sure you deal with item potency. And by that, I mean, you may have duplicate events describing the same thing going on the event bus. So you don't want to, you don't want to make sure, you don't want to allow that redundancy to have some kind of undesired impact further downstream in your event processing pipeline. So that's how we publish the events. The other thing we have to make sure we do from a security side of things is to give Amazon EventBridge permission to invoke those Lambda functions. We do that by creating a role. We essentially say, okay, so I'm giving Amazon EventBridge, which is denoted by the service, the principal service, events.amazonaws.com. We're going to give that permission to assume that role. And then the policy of that role itself is basically saying you can invoke the Lambda function, right? So fairly straightforward. But without this, what you end up getting is the rules will be matching. EventBridge will be matching your rule patterns. But if you haven't given EventBridge the permission to invoke the Lambda function, then really nothing is going to happen with the matching of those rules. So make sure that you do set up the appropriate policies for EventBridge. So the key limits we need to be aware of when working with EventBridge. So per AWS account, you can have no more than 100 event buses. There is a limit in terms of the number of put requests per second, and that is currently 400. However, remember, each put request, which is put events, can put an array of up to 10 events per request. So keep that in mind. So, theoretically, you can put 4,000 events on the event bus per second. 2048 characters roughly is the upper limit for the maximum event pattern size. We can have 750 target invocations per second. Per event bus, you can have 100 rules. And for each one of those rules, you can associate up to 5 targets. So they are the key limits that you just need to be aware of when working with EventBridge. So let's have a look at EventBridge from the context of the AWS console. So here's the event buses page. You'll see the default event bus that we talked about earlier on. This is always going to be there, whether you're using EventBridge or not. And you can see our banking demo event dev event bus that we created earlier on with the AWS command line interface. Okay, so here's the example of EventBridge rule. So here's the application approve rule that we also created earlier with the command line interface. Note the rule name, application approve. The status of the rule is enabled, which means that if any events come in to match that, any targets, and you see at the bottom here, we see that we have the Lambda target associated with that rule. So as I said, if any events come in that match this pattern, in this case, the pattern is saying, if my detail type key is application approved, I'm going to run that function, that target function, which is the bank account service function shown at the bottom there. So really, this is how you can go into the console, play around with things. You can configure everything that I've just done from the command line interface using the console. Now, if you find you set everything up, you've created your bus, you've created your rules, you've associated targets with your rules. It's all good. You're publishing events. You think everything's all good, but nothing is happening. Now, we talked about security earlier on. Security is probably the first thing that you should go to if you're having problems with target functions not running or step function workflows not being kicked off and so on. But what I like to do is go into the console for CloudWatch metrics and just turn on my event buses that I have configured just to see whether we have any failed invocations. Because if you see failed invocations, it usually means that there's the rule is matching, but there's something wrong with the target. In our case, for the banking application, we're not able to invoke that Lambda function, which, as I said, usually means you've probably got something set up. Either the ARN of that Lambda function is incorrect, or there could be a bug in the configuring the aspect of your security. There probably may not be a bug in your Lambda function itself, because if the Lambda function exists and security has been set up, the Lambda function will actually fire. So from the event bridge perspective, the invocation was successful. So you should also check CloudWatch logs as well to make sure that the Lambda function associated with the target isn't actually running. If you see an item in there that denotes that function has been initiated, then from event bridge perspective, the invocation was considered successful. So if we look at event bridge in the real world, so obviously we have Datadog. Now we're actually going to be looking at sort of two SaaS integrations. SaaS integrations are a really popular use case for Amazon Event Bridge. So in this case, Datadog was enabling ticket prioritization and routing with the Zendesk Event Bridge integration. So what does this mean? So the Datadog Zendesk customer experience platform generates events, and obviously for their customers, they want to be able to do things with those events like further downstream processing. So what they used is the Event Bridge integration for Zendesk. When anything happens in Zendesk now, it generates an alert or an event. It goes onto the Event Bridge, and then they can do further downstream processing for their customers. In this particular case, obviously, we're looking at faster case resolution. So now, that's all very great, but there's huge benefits from this. One, they have more timely response to event activity, which means higher customer satisfaction. Engineers are spending, time solving actual customer issues rather than managing various integration and point-to-point APIs. And because we're not polling the Zendesk system, they're not hitting their APIs as hard as what would have been done in one of those traditional point-to-point integration solutions. Cox Automotive have also been doing something similar in the incident resolution space. So they've got faster incident mean time to resolution with the PagerDuty Event Bridge integration. So with this type of integration, when anything happens on PagerDuty, an event goes onto the event bus, what we can then do is trigger a Lambda function in response to that PagerDuty event, which can then grab runbooks and post details back to PagerDuty, helping us and helping Cox Automotive customers resolve their issues faster and creating a really good experience for their customers. So that's just really two use cases of Event Bridge with the SaaS integration that we talked about right at the beginning of the session. So if you do want to learn more about Amazon Event Bridge, I highly recommend the Intro to Event-Driven Architectures and Amazon Event Bridge, which is on YouTube. It's about an hour long. It's fairly easy watching. Obviously, we have the Event Bridge developer guides and frequently asked questions on the AWS homepage. So definitely check out those links to get started with EventBridge. Now, if you want to further or kickstart your modern application development journey, I highly recommend you have a look at the offerings from AWS Training and Certification. So we have training around developing on AWS. We have some certifications for DevOps engineer, as well as certified developer. So definitely, if you want to be relevant in the world of cloud computing, have a look at those. Have a look at those offerings. In addition to those links I mentioned earlier about getting started with EventBridge, and you'll be well on your way to modern application development, especially in the realm of event-driven architectures. So on behalf of Sean, Gabe, and myself, I'd like to thank you for attending our three-part session on modern application development. We hope you found it interesting. A kind reminder is that we would love you to complete the survey. Let us know what you thought of today's event, how we can improve the event experience for you in the future. So yes, definitely complete the survey. But we've had a lot of fun delivering or creating the content for the session and delivering this session. We hope you get a lot out of it.